true or false. In number 1 we got, for any scalar C, u dot CV is, just C outside, u dot V. Yeah, this is true. That is one of the properties of inner product. Okay, this constant in fact always can be pulled outside. Number 2, if the distance from U to V, okay, this distance from U to V is just norm of U minus V, equals distance from U to negative V. U minus negative V is U plus V. That is true. Then U and V are orthogonal. Is that true? I mean, that means U dot V 0. If this is true, does that imply U dot V 0? Okay, we need to work on this. Okay, so this norm is in fact square root of U minus V dot U minus V. If we square both sides, then it's that's gonna be without a square root, by the way. When we square both sides by the definition of norm, this is gonna be U minus V dot U minus V equals U plus V dot U plus V. Now we can multiply U dot U. Okay, these are vectors. Okay, I'm just being lazy here. U dot U minus U dot V minus V dot U minus plus V dot V. Okay, that's the left hand side. So let me use different color for right hand side. In the right hand side we got U dot U plus U dot V plus V dot U plus V dot V. Okay, and U dot U is in fact norm U squared, but U dot U from right side and left and right side cancel, and here, and we know that U dot V is same as V dot U. Okay, this dot product is just commutative. That means we got U dot V, so negative 2 copies of U dot V is equal to 2 U dot V. Now we can add so that we get 0 equals 4 U dot V, and we can divide both sides by 4. That implies U dot V equals 0. So the distance from U to V, so U minus V, norm U minus V equals distance from U to negative V, U plus V, and we did all the work. We square first. If we don't square, we get a square root. Okay, and we got U dot V equals 0. So this implies U and V are orthogonal, and that means true. Okay, number 3, if vectors V1 through Vp span subspace W, that means every single vector in W is a linear combination of these vectors. That's the meaning of spanning. So these vectors, these P vectors span this subspace W, and if X vector is orthogonal to each Vj, so we got 1 through P, so X is orthogonal to every single spanning vectors. That means X dot V1 is 0, X dot V2 is 0, all the way to X dot Vp is 0. That's given. Okay, then X is in W perpendicular to this. Yeah, that's true, because V1 through Vp are spanning vectors of W. That means every single vector in W is a linear combination of these, and X is orthogonal to each of these. That means X is in W perp, orthogonal to W. That's true. That's by definition now. We just by a theorem. For any scalar C, norm or distance CV equals CV. That's false, because by the property of norm, CV is, when we take this out, it becomes absolute value of C. Okay, it could be negative, but when we take outside, it must be positive. Okay, that's why it's false. Here u square plus v square, norm u square plus v square equals u plus v square, then u and v are orthogonal. So I'll leave you the work pretty much similar to number 2. Okay, and it's gonna be true. In fact, look at the left hand side is just that. Right hand side, when we do this, this is u plus v dot u plus v. And when you take this dot product, you're gonna get u square plus 2uv plus v square. And u square cancel, v square cancel, you get 2uv equals 0. That means u dot v equals 0. That means u and v are orthogonal. We know that u dot u is norm of u square, by the way. Number 6. Not every linearly independent set in Rn is an orthogonal set. Yeah, that's true. We can have linearly independent set, but that's not orthogonal. For easy example, 1, 2, 3, 4. Okay, this set is linearly independent because we got only 2 vectors, and that's easy. The second or first vector is not a constant multiple of second. In fact, one of these is not a constant multiple of another. So these are linearly independent, but orthogonal means when we multiply, we are supposed to get 0. But when we multiply 1 times, so 1, 2, dot 3, 4, when we multiply 1 times 3 is 3, plus 2 times 4, 8, that's 11, that's not 0. So these are not orthogonal. So not every linearly independent set is an orthogonal set. That's true. Number 7. The orthogonal projection of y onto v. So let's look at here is v, and let's say we have y somewhere. Here is y. Orthogonal projection means we just drop a perpendicular line. Okay, then that gives us a vector here, and that vector is in fact projection of y onto v. Okay, this from here to here. So that's the given part here. The orthogonal projection of y onto v is same as orthogonal projection of y onto CV, where c is not equal to 0. So if we multiply v by a constant c, if up to here, if c is bigger than 1, it's going to be longer. Okay, c bigger than 1, so maybe like this is CV, but the projection is the same. This is the same projection. It could be shorter, or even sometimes on the other side, still the projection is the same. This is true, by the way. Okay, we can have, here is y and here is v. When we multiply v by negative number, it's going to be here. CV is here, but the projection is always this vector. Okay, this vector. So this is true.